All right, how to stabilize carbocations. How to stabilize carbocations. Well, there's 3 ways to stabilize carbocations. And these are listed in increasing order of importance. The first way is something called hyperconjugation. The second way is pi bond resonance. And the best way is lone pair resonance, because that lone pair resonance often gives something that has a full octet. It can give resonance structures that have full octets. So let's take a look at each of these and how they work and break it down. So we've all learned this fact that tertiary, secondary, and primary, right? These carbocations, tertiary is more stable than secondary, which is way more stable than primary. And the reason that is because of hyperconjugation. So what is hyperconjugation? Hyperconjugation talks about these sigma bonds that are 2 bonds away from the carbocation, or from the plus charge, right? From the plus charge. These sigma bonds can help stabilize that carbocation. And the more sigma bonds that you have 2 bonds away, the more stable your carbocation can be. Tertiary has 1, 2, 3, 4, 5, 6, 7, 8, 9. I call them hyperconjugation buddies. Right? It has 9 hyperconjugation buddies. Sigma bonds, 2 bonds away from the carbocation. A secondary has 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And a primary one would only have 1, 2, 3. 9 is more than 6, which is more than 3. 9 is better than 6. More hyperconjugation buddies, the better. Now, what does this actually look like with a molecular orbital picture? So imagine there's your carbocation. All right, so there's your empty carbocation. And sigma bonds are 2 bonds away are 1, 2, 1, 2, 1, 2, 1, 1, 2, 1, 2, 1, 2. So there's 6 there. And then 3 more here, right? It doesn't matter if it's sigma bonds to hydrogens or carbons. Just sigma bonds, 2 bonds away. So this has 9 hyperconjugation buddies. The way I like to think of it is, right? There's electrons in this bond here, right? And it's not perfect, right? So here's your carbocation. It's lined up perfect. And your hyperconjugation buddy, right, is kind of like off at an angle, because this is sp3 hybridized. And the bond angles for that are 109.5, right? What's the bond angle here? It's 90. So they don't quite match up, right? They don't quite match up. Could this do resonance? No. But is it sharing a little bit of this electron density, right? A little bit, and so it's helping a little bit, right? All of these 9 sigma bonds, 2 bonds away, are helping a little bit. So it helps, but it helps the least, right? Because of course resonance, which we keep coming back to, really stabilizes things, right? And that's what's the next best thing. So hyperconjugation is not a perfect overlap. Electrons don't move. No electrons are moving in hyperconjugation. No electrons are moving in hyperconjugation, right? But it helps stabilize a little bit. Foreshadowing, when you start thinking about rearrangements, though, think about this methyl group just jumping ship, right? When it jumps over, that's kind of like hyperconjugation to the extreme. That's a rearrangement. But we'll get there in a second. So what about something number 2, pi bond resonance, which is more stabilizing than hyperconjugation, because with pi bond resonance, we're actually moving the electrons around. We're actually spreading out the charge. So since we're going to do some resonance, let's number our atoms so we don't forget anybody. All right, this allylic carbocation. This is an allylic carbocation. It's a secondary allylic carbocation. And do a resonance form. Plus charge there. That's on carbon 1 now, 2, 3. This is a primary allylic carbocation. Which one's more stable? The secondary one. Which one maybe leads to a more stable product? Right? If a nucleophile were to come in here, This one will lead to the more stable product, right? Remember we talked about kinetics and thermodynamics and stability of intermediates versus stability of products. So thinking about those things. This is pi bond resonance, right? Either way, it's a good thing to happen, right? It's good to spread out that charge. So that's pi bond resonance. That helps stabilize carbocations. All right, so our final way to stabilize carbocations is lone pair resonance, and this is the best way. Because what's going to happen here, a lone pair is actually going to do resonance, and it's probably going to make it a situation where you don't have a carbocation anymore, and every atom has a full octet. And of course, the octet rule is the most important rule. So I could draw a resonance form here. Electrons go there. And with our advanced understanding of chemistry, right? 1, 2, 3, 4. We know that this second resonance structure is actually a better resonance structure. Why? Everybody has a full octet, right? So it's a major contributor. Now, though, somebody should say, well, wait a second. But we're learning about reactions. Exactly. So this might be the major resonance structure, but which part of this molecule is the electrophile? Which atom? 1, 2, 3, or 4? Put it in the chat. 1, 2, 3, or 4. All right, so this is tough because we're so used to saying charge bad, right? But then you got to stop and kind of think about the chemistry that's going on here, right? You know about polar bonds. Carbon-oxygen bond, right? The oxygen might have a formal plus charge, but this is the carbon that's electrophilic, that's electron deficient. This is the electrophile. Carbon 2 is the electrophile. And actually, this resonance structure helps us see that, right? It helps us see that in a different way. Even though this is the major structure, it helps us recognize how things react. That's why resonance forms are really important. They help us understand how things react. Okay? Perfect.